Hey, welcome back to Math with Patrick. Today is November 13th, and we're solving problem 317 from the Daily Epsilon calendar. And the answer should be 13 because that's today's date. And of course, we have our helper Quill today helping us out with some of the math. So we need to find the sum of the coefficients of the odd powers of this expression here. Looks like we have some kind of quadratic, 1 plus x squared, and then we're cubing that. So the idea here is that if we just multiply all this out, we're going to get some kind of like degree 6 polynomial. I can kind of see that we're going to have x squared times x squared times x squared as our leading term, and then like this 1 times 1 times 1 as our last term here. Although we do want to learn more about the odd powers of this expansion. And so since this has a power of 6, I actually don't really care about that. Since this has, technically it's a power of 0, and 0 is an even number, I don't really care about that either. We're going to need to know the coefficients or those kind of multiplying numbers in front of our odd powers. Now, instead of solving this normally, though, I do want to solve this using a volume model rather, because we have this kind of power of 3 suggesting volume. But I do want to just show area models first, because that's like the usual. Like usually if you say multiply some kind of linear polynomial with another linear polynomial, you can think of it as like finding the area of a rectangle. And if you multiply all of these kind of parts together, or just essentially distribute all the things that need to be distributed, then you can get basically the standard form polynomial instead of, say, the factored form that we would start out with. So like reading it like this, it's kind of like we have a length and a width for a rectangle, but then we can multiply out all of the parts, and then we can rewrite it as something like this. And so this shows me that this factored form and this standard form are the same, and an area model can be pretty useful just to make sure that you're multiplying all the right things. For example, like if we had more terms in our factors, I guess, say we have a trinomial instead of a binomial, then using this area model is nice because we can visually see all the multiplication that needs to be done. Here, though, since we are cubing something, this would actually look like a volume model. I rarely ever do this just because if you're trying to draw 3 dimensions on a page, which is 2 dimensions, it's a little bit hard to do that. But I think I have a convincing argument for this particular problem, even though it's going to be a little bit hard to spot all the different parts of my volume model. So the reason why I have like these lengths here kind of in groups of 1, 2, and 3 is because we have 3 terms in our factor here. And then the reason why it's a cube or in 3 dimensions is because we are raising it to the power of 3. And so each of those 3 dimensions, the length, the width, and the height, can be represented by this x squared plus x plus 1. And I'll just say that maybe this top left box is going to be where my x to the power of 6th was earlier. So I think I should organize it with x squared here, x and then 1, x squared here, x and then 1, and then I also need that kind of depth here, so x squared, x, and then 1. And we already kind of covered how x to the 6th has an even power, so I don't really want to count this box in my eventual standard form. And then also we can kind of see over here, this box back here is furthest in the back, it's furthest to the right, and it's in the bottom layer. And so that box represents multiplying that 1 times 1 times 1. And as we look around this, essentially a Rubik's Cube, we can count up that there's 9, 18, and then 27 total squares, or rather cubes. And I'm going to see if I can essentially color code the cubes that I want in green, the odd powers, and then, as I have been doing, color code the ones that I don't want, the even powers, in red. So this box, I don't think I want this one either, because this one represents doing 1 times x squared times x squared. We would get x to the power of 4, and and that's an even power. And I think the general rule here is as long as I hop 2 boxes away, then I'll find another even power. This one right here looks like it's just going to be an x squared times 1 times 1. And so we would just get an even power in there. And I'm starting to see this kind of visual pattern show up in our volume model here, where there are just certain boxes that I do want and certain boxes that I don't. And if you wanted to, you could kind of double check why these ones should be shaded red. But, I think I missed this one in the middle here. And I think I missed this one here and this one there. There we go. And I think this about does it. And so all the other boxes should represent one of my odd powers instead. And so we can see in this kind of top layer, we do have 4 parts that I do want. In this middle layer, it's hard to see, but we do have all 4 corners. And so there's a corner kind of in the back that you can't see, and also the very, very center box, which represents doing x times x times x. That's also going to have an odd power, but you just can't see it in this picture. But there are going to be 5 boxes in the middle. And then finally, just like the top layer, the bottom layer is also going to have 4 different boxes that represent multiplying something to get to an odd power. And what's kind of neat about the things that we're multiplying is that all the coefficients here are just 1. And so all of these green boxes are going to have a coefficient of 1. It's either going to be like 1 or 1x. Actually, not the number 1, because again, that's an even power. It'll be like 1x, 1 cubed, or maybe 1 to the power of 5. Sorry, 1 times x to the power of 5. And all of these coefficients, rather, in all my boxes are just 1. So when I add up all of my x's, add up all of my x cubes, and add up all of my x to the fifths, all of those 1s are just going to add up, and they're going to be the sum of the coefficients of all the odd powers. So I can just add up all these numbers. 4 plus 4 plus 5 is 13, and this is my answer. I don't actually really need to know what the actual coefficient is in, say, that kind of standard form after we combine all of our like terms. I just know that we're going to have some amount of x's, some amount of x cubes, some amount of x to the power of 5s, and they are just these green boxes, all 13 of them that I colored in this box. So hey, maybe if you wanted to, you could expand it out the normal way, right? Maybe multiply 2 of them together first, and then multiply the third one. But I just didn't really feel like doing all that algebra, and I much preferred thinking about this as a volume model. So there's my answer, there's my solution. Hope you enjoyed, and I'll see you tomorrow. Bye.